好。So first I would like to do the announcement for the final report. And here's the deadline for the final report. It's the 23rd on Tuesday of June. So the deadline is, I should specify it clearly. This is better. We start to accept the submission from 17 in the afternoon, and we wait here for a half hour. So please print your report, bring it here. Print your report, staple them together, and bring it here in this room, SA320. I will ask the TA here to collect the report, and printed version is accepted. And we don't take electronic files because it leads to a lot of problems. It's better to have a paperback record. And you know that we started the semester late in the half year, and now we have a very short time to do the calculation for your credits. So unfortunately, this time we are not able to give you any extension to the deadline. So please submit your report on time, and this time we are not going to have any extension. 然后先跟大家说那个期末报告怎么交。好，deadline 是6月23号星期二。然后呢，请你在下午5点到5点半之间到这间来，然后我会请助教在这里等，会在这里收报告。那请大家把报告印出来以后，然后钉起来，然后呢交给助教。然后呢，这次我们不收电子档，因为收电子档的话，在一个人很多的班级，有时候会出一些很糟糕的问题，就比较麻烦，所以我们只收纸本。然后呢，再来是这次大家知道我们整个学期是延后2个礼拜开学嘛，那我们要上传成绩跟计算那个成绩印成绩单的时间就变得很赶，那我们这次就没有办法给大家一直往后让deadline变得越来越晚，就这次比较没有办法，所以请大家就是准时收。那超过时间我们就不收喽，就拜喽。这次我们会非常坚决的就拜拜这样。好，所以就是下午5点半以前一定要交过来。然后呢 ，and then here's the submission of the bonus experiment report for the student who is interested in making the electronic motor. And if you did the experiment report, if you write it in the report format, and please just print it and submit it with the final report together. And the deadline is just exactly the same, and the rules is just exactly the same. 那有兴趣已经做过那个电动马达，或者还有兴趣想要补做的同学，那就是你们就把实验报告写好以后，就跟 final report 的同个时间一起交回来。那截止日期就是一模一样，然后规则也一模一样。好，所以就是有兴趣的同学你可以交过来。那这是关于期末的。接下来，比方说检查成绩啦，然后什么时候送成绩，我会再公告。And then in the following days, so the time that we will post your credits on the website, and what is the time for you to do the checks, and what is the deadline for credit submission, and I will do announcement on the website later. Okay, this is the announcement for the final report. And this is the schedule for our movie theater. So this is the June 19th, this Friday, and we are going to play the movie. This is from Ghost in the Shell, and it's originally a television series. and it's called standalone complex, but they just take the most important part of the story and recompose it, edit it, and just merge them into a movie. And the movie is called The Laughing Man. It's a very long movie. It's about 2.5 hours long. So we will start earlier. We start from 10 o'clock, then I'll start to play the movie. And in this room, then I just keep playing, and I would expect it stop at something like 12:30. So if you would like to have brunch, if you would like to have lunch, and then you can just prepare it and you can take it here. Okay, and this is a very good movie. But today we don't have that much time for chats because I have to run through the quantum mechanics today. 好，就这是星期五要看的电影，那我们会从10点开始放。我很节制的讲到这里就结束，因为我们今天要赶课。好，欢迎来看电影。那我们要开始标量子力学了。This is quantum mechanics today, and before I really start the quantum mechanics, maybe just a remark for the Bohr's model. 好，没关系，算了，不讲了。好，okay. So in the chapter for quantum mechanics, if you remember, we just talked about the matter wave last time, and we saw that we actually can use the mathematics of the waves, and we can compose waves with various frequencies, and then we can make a bunch of localized wave. We call it a wave packet, and the wave packet is actually can be treated as particles. So that is now our mathematical tool is done. And now how do we use it? And I'm sure everybody knows that we have two representations for wave functions of the matter. One of the representation is just the waves, so we can just solve it with partial differential equations, and that was developed by Schrödinger. And another representation is the matrix representation, and matrix representation is, I think it's very hard to operate to me, because it's very abstract, and it's a little bit like making up answers, and it's not really like you can see the possibility distribution. So that is for theoreticians and for those who are working with energy bands. Okay, but anyway, it's developed by Heisenberg. Okay, and we are going through these two mathematical tools, and I will show you why the two representation are equal to each other. 好，那我想大家都至少都有听过，就是量子力学它有两种表现的方法，一种是薛定谔的波函数，另外一种是海森堡的矩阵表示法。那么我们会从波函数开始，然后最后我会再给大家看说为什么波函数跟矩阵两种数学的工具，他们在讲的是同一件事情。但是海森堡的矩阵，我觉得比较难在普通物理的阶段说明，因为它其实是一个凑答案的结果。就是我们已经知道氢原子的能阶是怎么分布的，海森堡就凑答案，凑一凑，他觉得用矩阵 OK 可以，所以其实它并不是一个很有物理、很物理的东西。那我觉得用矩阵入门的话，很容易会造成很痛苦的感觉。那我们也从波函数开始讲 ，we start from wave functions, and this is Schrödinger, and this is his definition for the wave functions. So he just said that if we use the matter wave to describe the position and momentum of your particles, and we can define a wave function, and now we are using the form that we are very used to. So this is the exponential ikx, and you can expand it to the cosine and sine form. So you can see that, oh, this is a kind of oscillations. And if you would like to construct a wave packet, then you will have multiple A's, multiple amplitudes, with multiple K's. K is the wave number, so that is your ways to construct a wave packet. And how is the wave function related to reality? And Schrödinger said that he thinks the wave function is related to the possibility of existence, and just as we saw on the diffraction experiment for electrons. So we can, and he just said that, okay, anyway, I just define a wave function, and I just define that the square of the modulus of my wave function, and if I do the integration, and then it should be equal to the probability in the space. So this is Schrödinger's thoughts. And here we have to take something like an absolute value, is because when we are really operating the exponential ikx, and sometimes we will have imaginary parts. So then we have to do some mathematical tricks, and then we can understand that it is something like oscillations, and then we are taking the amplitudes at the end. Okay, so this is the definition of wave function. And this is how the mathematics generally go. So we know that the distribution of the possibility as a function of place is just equal to the square of the absolute value of our wave function, and then this is just a small pieces of the area under the curve. So the blue line here, this is the wave function squared. So this should be the probability. And this is the position from 0 to somewhere, and here is the distribution of the probability. So if you have a bunch of electrons and then they just pass through a kind of gratings, and you can count the numbers of the electron passed, then this is, if this is something that you get, if this is something that you measured, then you can know the distribution of the probability. And this is like, if you would like to, now we have to do something like a double check. Because if you integrate over the space, and the probability should be equal to 1. So every time when you thought of a wave function, or every time when you would like to make an educational guess of your wave function, and you have to do this check. 那大家就是这边我用中文稍微讲一下，就是你可以思考一下，我们之前在解偏微分方程式的时候，我们常常会做一件事情，就是 educational guess， 就是你因为经验的关系，所以你先猜一个解大概的形状带进去 ，OK 吗 ？OK， 然后我们就开始做一些检查，然后去调整一些参数，让它符合边界条件的期待嘛。那我们在处理波函数的时候呢，我们的思维逻辑技巧就是一样的。And if you remember when we are solving the partial differential equations for the oscillator, and we use a lot of experiences. We have the experiences, and then we can guess that and this might be the combination of a sine function or a cosine function. Then we construct it in a form. We plug it in back to the partial differential equation. We see if it matches or not. If it matches, and then we start to play around with the constants. And for solving the Schrödinger equations, and we are just following exactly the same technique. And so that's the reason why we have to do the probability check. So here's the check of the probability. We need to integrate our probability over the space from very far away to another very far away. But we have to make sure the probability should be 1. So only the wave functions that satisfy this condition can be the wave function for the Schrödinger equation. And here's another thing in statistics. So in statistics, when you are, for example, now it's like for example, if you have a lot of electrons, you send them through the gratings, and you expect the peak of the probability should appear somewhere. So if you are using this kind of thought, then we say mathematically that we are calculating the expectation value, 期望值. And in statistics, if you have a probability distribution and if you need an expectation value, and we are operating the wave function this way. So we have the wave function, we take the conjugate of it. You can remember the complex analysis. We take the conjugate of it, and then here's the original wave function, and we just put the value that we would like to expect at the center of them. And then you can first you calculate the phi star and x and phi, and then you do the integration again. So this is how we calculate the expectation value in statistical physics. And the expectation value can have many targets. We can expecting something with the locations, expect a momentum, we can expect any kind of probability of the particle. So if you are doing the expectation for the other thing, and that other thing can be a function like f of x, and it's just the same, and this is the way that you do a expectation value for it. And sorry, I think this is wrong. I have to correct it. No, this is not 1. This should be another value. Sorry, when I was writing the functions and I'm just copying it, you can see it. 不是这样，对不起，我写错了。Okay, so the answer here depends on the distribution of x, and the answer here depends on the distribution of f. Yep. And the only rule that you can check is if you take the wave function and then if you calculate the total probability, and then you should get 1. Okay, so this is the logic behind it. And then we can work on an example. We can work on the particle in a box. So first we do the box this way. So when we are analyzing a kinetic system, we care about the kinetic energy. There is a kinetic energy K inside. And we care about the potential energy. So this is the potential energy U. Sorry. A particle in a box is a model that we imagine. We have a particle that can move around. And of course, the particle itself is described by the wave packet, if you remember, the wave packet that we derived by de Broglie. And for now, the particle can only move in a range from 0 to L. So in that range, the particle can move around. And outside of the range, the particle is not allowed to exist. And the term the particle is not allowed to exist to set up a boundary condition like that. And we just set the potential energy U to infinity. So this is how we set up the model. Particles are not allowed to exist. Okay. Then now the particles are not allowed to exist because here are the particles and you have some kinetic energy, and if you somehow put in the energy in it and let it run faster, but because the U is very large and the particle is not possible it's not possible for the particle to have enough energy to be larger than the U and get out of it. So that is why we set the potential energy to infinity. And now we are interested in the places of the particle in the box. And the particle can be running like this, can be running like this, and can be running like this, isn't it? And what are the and you can think about it as a vibration actually. So what are the modes of vibration of the particles inside that kind of box? Okay, so this is how we set up the models. And because we can think about the particles in one dimension, bumping left and right, back and forth, and then we can just set up that actually it's a gas. So here is the boundary condition. We just said that the wave function at x equal to 0 should be 0, since if it's here, right here, and the particle shouldn't exist here, it shouldn't stay there, it should jump away right away. And for the wave functions on the boundary L, it should be 0 too. And you can take that the phi squared is 0 again. So this is the boundary condition. And inside the box, we can model the movement of the particle with sine functions. And since we more or less know that it should be an oscillation, so we just simply set up the wave function as an oscillator. And now the oscillator has an amplitude. It has the sine function and 2 pi x over lambda. The x over lambda is the wavelength of your oscillation, and x is just the position. So this is how we set up the model for the wave function. And now we can first of all think about the boundary conditions. So this is our wave function, and if we make a detailed calculation here for this one, this is the boundary, and the boundary should be 0 by definition, and this is equal to the wave function, and on the boundary both conditions should satisfy. And in order to satisfy a condition like that, the 2 pi L over lambda here should be an integer number of pi. Okay, so you can put in the integer number of pi here into the sine function, then you always get 0, isn't it? Okay, and because the 2 pi L over lambda should be equal to n pi, so you know the condition for your wavelength. So this is the first step, that you can get an idea from the boundary condition. And n is 1, 2, 3, 4, 5, 6. Okay. And then we go on to the next step. So what am I doing here? Lambda. Oh, so this is the original wave function, and we know that this is the condition for lambda. And then we put it back to the wave function. We rearrange it a little bit. Now you can see that the wave function should be related to the width of your box. Should be related to L. Okay, now it makes sense. And here we have an integer number here. So this is related to the vibration modes. The modes for standing wave. And the n equal to 1, 2, 3, 4. The integer number is actually the reason why we call it quantum physics, quantized. So 1, 2, 3, 4, 5. Okay. And now we have to do the check. Let's check the probability of it. So this should be the form of our wave function. And now we do a replacement for the parameters. So the wave function squared, and if we do the integration over the box, we can directly jump into the conclusion. We expect it to be 1. And let's check what are the conditions that matches our expectation. So here's a squared, sine squared 2 pi xl is just the same. We're just plugging it in here. But now we have to do a little bit of trick. We just defined n pi x over L as u. And here we have to replace all the dx into du. And here's the equation for you to do the replacement. So, wow, what am I doing here? Oh, what I'm doing here is the du dx. I just take a derivative on u, and the x just disappear and n pi over l. And then I move the dx to one side and the other parameters to the other side. So L divided by n and pi and du. Okay, so this is the relation between dx and du. Then we just replace the dx by this one. Okay, so then L and n and pi, they are constant, so we can take them back. Okay? We can take them out from the integration. And here's another trick about the trigonometrics. So if you would like to do the integration of a sine squared something, then you can do the replacement like this. Usually we do it this way because it's easier to do the, you can check the table for the table for integrations, and they will show you the answer, or you can derive it by yourself. And then basically that's it. And if we do 1 over 2 u, and the integration over u, and you can just replace the L by this one. If you do the replacement and if you do all the calculation here, I don't go into the details, you can check it by yourself. Then finally we can prove that the a squared here should be equal to 2 over L and take a square root. And then our phi satisfy the condition for probability. And another thing to remind you is that we have the integer number here, n is equal to 1, 2, 3, 4, 5, and then we have multiple solutions, and for each solution, and we have an individual index for them. So this is the reason why the wave function here have another n on the subscript. 好，最后一个我用中文特别讲一下。你会发现，因为我们的解里面，这就是一个解。我们的解那个 n 有很多种可能性嘛，1、2、3、4、5、6、7、8都是整数。那你有这么多可能性的话，我们解出来的波函数，这里你就要帮它打一个记号，就是 n 跟这个 n 两个要同步，这样大家就会知道说，哦，所以你的解有很多种可能性，这些解都可以，都符合边界条件的期待，也符合probability function 的期待。好，所以我们现在两个期待都符合了。And this is the graphical representation of our solution. So we have, this is the mathematical representation, but if you draw it into graphs, you can see that if we have n equal to 1 and 2 and 3, and you can go on, and I just draw the first 3 levels. So we have modes of standing wave. Yeah. Here are the modes of vibrations, and they are vibrating in a way like a standing wave, because the two ends of them are fixed because of the boundary conditions, and the vibration here they have the standing wave modes, and that is the reason why we have to quantize the solution. And for the probability distribution, then just take the wave function and take the absolute value and do a square root of it. Then you can see, oh, so this is the distribution of the probability. And for the level 1, 2, and 3, and you can see that the particles, for example, like the level 1, and the particles are more probable to stay at the center of a box. And if it has higher energy and you go to the second level, then here are 1 and 2 possibilities of the distribution, and if it has even more higher energy, then it has 3 peaks. Okay, so this is the solution for the particle in the box. So generally, this is the model for almost everything in crystals and in atoms. 那大家可以看到说，其实这个解我觉得就是一个非常简单的。 但是在物理学上面几乎不会跳脱这个模型，很少，几乎不会跳脱这个模型，就我们都会用这个模型去解晶体，因为晶体你可以想象，如果我有很多个盒子，很多个井，然后我把它一直往下面排列，然后那个其实就是它就是一个周期性的解法 （periodical solution）。然后呢，任何跟orbital 跟轨道有关的，所以它在原子分子物理里面常常用到。所以 particle in a box， 所以虽然你觉得它看起来很简单，但是其实概念就这样，概念它不会改变太多。Okay, and now we are working a little bit on the particle in a box for the hydrogen atom. Okay, I hope this is not too fast. So for the electrons in the hydrogen atom, we care about the momentum of it. So this is the h over lambda. This is by the definition for the matter wave. And then the lambda, we just know that here's a condition for it. And lambda is generally fixed by the width of your box. This is the Planck constant, and this is the quantized number. Then you can do a little bit of arrangement on it. And if we would like to know the energy, the kinetic energy of your spinning electrons, then you just take 1 over 2 m, and this is the velocity squared, and then you can convert it into p squared over 2m, and then just put the p in, and then you can have the energies. And because of the n is equal to 1, 2, 3, then you can have the energy levels. So this is how we get the hydrogen atom, purely theoretical, purely from the wave functions. 好，所以我们今天你要一下就很猛的，我们直接用 particle in a box， 然后马上瞬间，然后就把氢原子模型的轨道都推出来了。好，所以它的概念大概就是这样。Okay. And here is, okay, then this is how it is related to the results of the spectrums. You just see that we have energies. This is the energy. And L is actually related to the length of your orbital. And this is the mass. Okay, so the mass of the electron is very important. Then here is the N, and N is 1, 2, 3. And this is how it is related to the energy levels of the spectrum of a hydrogen atom. And if you really measure the spectrum of light emitted from the hydrogen atom, and then you can see spectral lines. And here, if you calculate the energy carried by the photons, then you can see they have a distribution like this. And if you pay attention to the distances between the spectral lines, and then you can see the dependency like 1 and 4 and 9 and 16 times of the original value, and that is just related to what we just derived, and this is related to the n squared here. 我看一下我有没有好。我们之前上课的时候已经给大家看过那个氢原子模型的光谱，所以我这边就不再重复了。那个光谱线，然后你去观察那个光谱线之间的距离的时候，你就会发现，它们之间的距离是从零完全没有能量到有一份能量。那时候大家都还搞不清楚所谓的一份能量到底是多少哦。然后呢，但是它的第2条光谱线。然后呢，就会变成4倍，就是第1条光谱线的4倍。然后第3条光谱线会变成第1条光谱线的9倍。所以那个时候大家就觉得，这个数字好奇妙哦，那样呢？然后他们就是波尔他先用旋转的轨道模型，他先推出了一个大概的想法嘛。那薛丁格在拓展他的数学模型的时候，他的第一个挑战就是他要用他的模型呢推出跟波尔一模一样的结果。 所以这就是为什么我们通常都会从 particle in a box 开始。And why is the particle in the box related to hydrogen atom? So you can see that although we started from a one-dimensional box, and the potential energy was set to infinity, but if you just sort of bend the one-dimensional axis here and reconnect the 0 and L together, like the paper bands here. So it's like one particle in the box, box number 2, box number 3. And then if all of the boxes are just reconnected together, and actually we are just forming a periodical boundary conditions, and the period of your wave functions really depends on the length of your box. So this is how we think about it. And since the length of the box is finite, then the wave functions that matches the boundary condition is limited. And that is a very strong supporting result for the single spectral lines. So if the particles are not distributed in a quantized way like this, when we look at the spectrum, we should see something like a rainbow. And it's a lot of colors, and here's another consequence would be like the electrons will be attracted by the protons, and finally it just spins in a helical way and bump into the protons. But when we look at the spectrum, it's not like that at all. So this is a very supportive experimental results for Bohr's model and for Schrödinger's particles in the box. 好，那么再补充一下实验上面的事情哦，就是 hydrogen atom 那个时候大家看到氢原子光谱的谱线的时候，大家震惊的点在于说，你如果把光谱画出来，光谱我们通常是画通常啦，做实验画完它会是 wavelength， 波长，然后再来是 intensity， 然后你要做一点就是你要做转换，你要把波长，然后呢，转换成频率，然后再乘上Max Planck constant， 然后变成能量。对，那你换成能量之后呢，它那个光子的分布就会变成一条线。那我们那时候大家看到那个线这样一条一条的，它是有一个很固定的波长，然后呢，波长1号跟波长2号中间什么都没有。这件事情让大家觉得非常震惊，因为以拉塞夫的那个布丁模型来讲的话，我们大家会觉得说，我的光谱应该要是连续的，就是会长得像彩虹一样。然后还会有另外一个问题，就是如果你的电子可以随处移动的话，就算它一开始是旋转类型的，但是呢，正电荷跟负电荷就是电子跟质子嘛，它们彼此之间会互相吸引，然后那个电子无论如何都越来越接近你的 proton， 然后两个就相撞，然后就没了。对，那所以大家会觉得说，有点怪怪的。但是看到氢原子的模型，看到那个谱线这样一条一条，而且它一条一条谱线之间还有这种1倍、4倍、9倍、16倍之间的差别的时候，那波尔就觉得说，他觉得应该有轨道。那虽然他那时候想的那个轨道的想法后来也被推翻了嘛，因为就是不确定原理，然后还有 probability distribution， 后来那个想法被推翻了。但是因为实验结果就是铁的，就是这样啊。那薛定谔他的挑战就是，他认为轨道模型不对，可是他必须要用他的波函数重新去证明说他的波函数也可以得到跟实验一模一样的结果。那这个就是他的答案了。好，我个人觉得非常的可爱。I find the approach like this is very cute and very creative. So, Schrödinger is an interesting guy too. he is very philosophical. He is interested in so many things, and on everything, and he have kind of very extraordinary opinions. And he always use his physics on problems which is very hard to solve. For example, he just completed the wave function representation for quantum mechanics, and then he is very interested in the physics of life, the physics of biological effects. So he started to make some assumptions, and then he started to explain what is the difference between life and matter, and he tried to answer this question from thermodynamics, from classical dynamics, and from some other aspects. And he has a little book, What is Life? But I find the Chinese translation really awful, so I didn't really finish reading it by myself. But when I find a good translation, then I will read it. It was originally written in German, but sorry, my German is not good enough to read it. 就是薛定谔是一个很可爱的人，他对什么事情都有兴趣。然后他是一个他的物理学的一些基本的想法很好嘛。那我觉得他很强的地方就是他很擅长设定有效的假设去分析困难的问题。比方说，他其实我觉得quantum mechanics 应该算是对他来讲应该就是基本功。那他有做过一件大家觉得很有趣的事情，是说他想要回答生命是什么这件事情，就是生物跟物质的差异到底在哪里，怎么来的之类的。那它里面有一个说法还蛮有趣的。他说生命体，你会发现生命体它会一直就是你看一些什么细胞组织，或是你看一些化学反应产生的过程，就是生命体它会一直创造出一个秩序，它就是一个想要抵抗变乱的过程，然后它就是违反了热力学第二定律之类。他很擅长用这样子的想法去解释一些很困难的问题，对，那所以他还蛮厉害的。但是那本书他写了一本小说，其实是演讲集，然后那本书。我觉得他的中文翻译很糟糕，就是很难理解。对，然后他的原文是用德文写的，可是我德文又不够好，对啊，所以以后希望可以有比较好的中文翻译，然后大家可以来读那本书。对，他真的蛮厉害的，大师，我个人还蛮欣赏他的。Okay, so this is generally the structure of Schrödinger equation. So he just simply followed the logic of classical mechanics, but he just changed the formation a little bit. This is actually called Lagrangian. Maybe it's not for you, but for students in physics, and we have to learn classical mechanics. And so basically we go further from Newton to Lagrange, Laplace, and other philosophers for physics. And the Lagrange just said that all of the mechanical systems is composed of kinetic energy, potential energy, and this is the total energy. And then if you follow a certain procedure, and then you always get the shortest path of movement. And Schrödinger is following that kind of thoughts, but he derived it for a quantized system, and this is his result. So we have a term for kinetic energy. This is the kinetic energy, and it's not very far away from classical one. So, but we have an h bar. This is to convert the wavelength to energy, the Planck constant, and this is mass, and there's a factor of 2. Done. And the potential energy can be anything, can be any kind of distribution, and the total energy. So it's not very far away from what we already know. So that's why his representation is very, very popular and easier to understand. And here is some conditions for solutions of Schrödinger functions. And if you are very interested in theory, and then you can go through it. In my opinion, we set up these rules for us to to make educational gas, but I think maybe these rules will be broken someday for people like Einstein or for people like Newton。这边有一些这个是到目前为止，就是大家在解薛定谔方程式的时候，那个解通常要遵守哪些规则，但是有兴趣的同学看看就好了。那除非你是要做理论的，除非你是要做什么固态物理的理论的时候，大家就会计较这个东西。可是我会觉得像这种规则类的啊，我们就会等待一个爱因斯坦可以把它打破。就是比方说，其中有一条规则，如果有人觉得说，不对啊，这个限制到什么东西，然后就会有一个新的爱因斯坦冒出来，就会把那个规则打破。我们的科学都是这样子进步的，所以这部分就是有需要的同学你再回去检查就好。Okay, and now I would like to introduce some common types of potential energy, and they were developed because of different reasons. So the theoretical physicists, and they just set up different kind of potential energy to model the things that they are interested in. We started from the deep well, this one, or orbit, and here is, then the other question is if the height of the potential energy is finite. It has a particular number. It's not that high anymore. And what if there are some possibilities that the particles can have a lot of energy and then jump out of the box? So this is the well. And here is another thing. So if you have the potential energy as just a wall, and the wall has a finite height, so if the particle is here, and if it gets enough energy and it can jump over the barrier and get out of it. So this is for the barrier, and this is the distribution of the potential energy. And then here is a very important one, the harmonic oscillator. So this is the potential energy, and the potential energy has a parabolic form. Has a parabolic form. And then we let the particles running like oscillator inside this potential wall. And this is very, very classical too. And actually, in most of the cases, if we have a potential like we have a top and to the bottom and then to the top again, no matter how it is distributed, and we would like to decompose it into many different harmonic oscillators, and you can continue with the modeling. Okay, so here are the 4 types of potential energy that is frequently used in quantum mechanics. And for the real quantum mechanics, then we have to take a lot of effort to solve the Schrödinger equation for each of the cases, and the solution was really, really complicated. And here's the graphical representation of the solutions. We just finished the deep well, and we have the standing wave inside. And then if it's a well and if it has a finite height, and then the consequence is that the particle will have some probability to get out of the box, and it's represented here by the little plateau here and this one. So this is the solution for the well. And if we have the barrier, then it's the famous case is that a particle can go through the wall by tunneling. So this is actually just a model for the tunneling effect. And for the harmonic oscillator, then you can think about it as the particle in a box, but the box has various lengths on different height, and then you should find the standing wave that matches into your potential energy. Okay, so here, this is now, I hope that you can understand when we are talking about quantum dots, when we are talking about TEM, the transmission, STM. Actually, we should, this is STM, scanning tunneling microscopy. 就是有一种电子显微镜，它是在测量这种穿隧调效应产生的电流，那个叫 STM。好，所以大家就可以知道说，哦，原来是在讲这个东西啊。Okay, and here are some examples in physics or in engineering, which is related to different kind of potentials. We just said that this one, the particle in a box, in a confined box, is just related to the hydrogen atom. And this one was related to the quantum dot. And here are some. What was really happening is by creating a kind of quantum dot with two-dimensional semiconductors, and we just let I think that was electron. They just let the electrons oscillate inside the quantum well, inside the potential energy, and when it oscillates enough, and here are some possibilities for the electrons or the photons. Sorry, I'm not very familiar with quantum dots, and if you're interested, you can read it by yourself. But so it's taking from the emitted light from the quantum well. And for tunneling effect, I just said that the scanning tunneling effect microscopy. And this is, and here is another example for this nuclear decay. Okay, so sometimes we just set the nuclei just the nuclei is here. And because of the combination of protons and neutrons, and they somehow form a potential energy like this, and we are calculating the probability of a alpha particle, beta particle, or gamma particle. What is the probability of them to run out of the potential wall? Okay, so this is related to the nuclear decay. Maybe they have some spectacular models. And for this one, that is related to the bonds between atoms. So actually here the potential energy was constructed by the two bunches of positrons. Yeah, we have a bunch of positrons and neutrons, a bunch of positrons and neutrons, and they create a potential energy like this. We just model it as a harmonic oscillator, and here are the wave functions for the electrons running between the two points, and they just run in the spaces, and they can combine the two atoms together. So this is a model for the bonds between the atoms. Okay, for the bonds between atoms, here is a very nice review, so if you have time, you can read it. And here are the pictures for what I just said. Yeah, this is the graphics for it. And why am I doing this? Oh, okay, and here is how we play with the coefficients and to completely match. Here we are matching the solutions from the Schrödinger functions to the solution by Bohr. So we are matching the solution from Schrödinger functions with the Rydberg constants. So this is also something, if you're interested, you can just study it. A little bit boring, but it's very important in physics. 所以这一段他在做的事情是从解薛定谔方程式开始，然后它的整个流程跟我们上课一开始的时候解那个柱波是一模一样的，只是它的常数就多了那个薛定谔加进去的常数，然后呢，你就是跟随着一样的步骤。解到最后呢，你会把薛定谔方程式的解跟雷德堡常数，就是可以比较这样，然后两个是一模一样的，所以这个过程是在做这件事情。好，就是一个对答案的过程，也是一样。有兴趣的同学可以自己回去自己看，这个在物理学上还蛮重要的。Okay, and here's the solution for particle in a well. And we have, so here's the situation, the total energy of the particle. If the total energy of the particle is smaller than the potential, then the particle is confined. And if the total energy is larger than the potential, then the particle is free. Okay. So then, because in quantum physics we are working on possibility distributions, and in this kind of cases there are some possibilities that the particle can get out of the box. It can exist somewhere here or somewhere here. So the solution for the sending wave somehow extended a little bit into the locations with the potential energy. So that is the only difference. And here are the little derivations. We start from the Schrödinger's function. So this is the Schrödinger's equation, and we have the kinetic part, we have the potential part, this is the total energy. And we just move, okay, we keep the second derivative part, and we move all the constants to the right hand side. Yeah. And here all of them are constant. Yeah, they are. All of them are constant. We just keep the energy as a constant too. So we just give it another name. So this is C. And here we have the old friend. So this is another second derivative, and then we are expecting something like an oscillation. So it's just exactly the same logic. Then we can apply the exponentials, but to be general, to be fair to all the possibilities. And here we have exponential Cx and exponential minus Cx. If you put this one, this is your educational guess, the wave function. If you put it back to the function like this, and then you will get both of them satisfying the condition. I mean, this one and this one, both of them satisfy the condition. So now, yeah, this is experiences too. There is no reason for it, but just by experiences, it's easier for us to solve it. We have three possibilities of the combinations. One possibility is exponential Cx, and here is another possibility, exponential minus Cx, and here's the possibility that with sine and cosine and combined together. So here are the three possibilities of solutions, and people just, after a very lengthy derivations and many trials and errors, and people just finally get into a stabilized form like that, and they can assign the equation, this one, for the places with x smaller than 0. So this one belongs to here. The wave function number 1 belongs to zone number 1, and number 3 belongs to zone number 3. And you can just by putting in numbers, and then you can understand the reason why. And then for the oscillations in between, we have the sine function and cosine functions. Okay, and here is a minus Cx, and actually, for example, if we assign the number 3 into the zone number 3, it's simply because we expect the wave function is going to decay in places with a lot of potential energies. So this is just I think it's a condition for the model to match the physical truth. Okay. So this is how we get the solution for a finite well. Okay, so here's a graphical representation of the solution. And of course, when we are constructing the solutions, we have to consider the phi number 1 and phi number 2 should have exactly the same number on the boundary. And we have to do the same thing for another boundary, and that is the trick for us to find the A and B and F and G. We have to find the exact number for it, but it's just trivial. It's just some technical work. 好，就我这边稍微说明一下。我们刚才非常快速的就是给大家看一下那个解就是解量子井的时候的流程是什么流程。那我们不走中间的 detail， 因为走中间的 detail 的话，你要检查的条件很多。对，那我可以跟大家大概说一下，我们基本上就是解都是用猜的。然后这些人他们在解这个量子井的时候，他们也是很多科学家，然后经过一个很长的讨论啊、吵架啊的流程，最后大家得到一个这样的共识。所以大家就觉得说，好，那我们的井的左边跟右边呢？因为我们刚刚看到说，哇，我们现在有3种可能性，那这3种可能性是不是一个区域你就认领一个回去啊？好像是这样齁。那我们来测试一下。那他们测试一下，如果我们这样子去安排的话，可以行得通然后呢，但是大家要注意的事情呢，就是1号解跟2号解在边界上面，它们的数字要是一模一样的。然后呢，2号解跟3号解在边界上面，它们的数字也要是一模一样的。所以这个是你可以根据你的边界条件的设定，然后呢，你就可以然后再经过那个 probability distribution 的 check。然后呢，你到最后你就可以把 A 是多少 ，B 是多少 ，F 是多少 ，G 是多少 ，K 是什么，你也可以从井的宽度，你就可以推测出来。所以基本上解薛定谔方程式的逻辑，差不多就是这样。好 ，OK， 给大家一个 taste。So I just give you a very quick review and a taste of it. And again, the tunneling effect, we are not solving it here. This is very difficult. It really takes a lot of techniques and a lot of hacks. But anyway, we can just show you the distribution of the wave function. Okay. But from the graphical representation, you can roughly get a taste. You can see that, okay, so the wave function number 1 is a sine wave. And the wave function number 3 is another sine wave. And the amplitude of the first sine wave is attenuated by the wall. So this is the attenuation. And the trend of the attenuation can be solved by the Schrödinger functions by applying the boundary conditions. And just the same, we just check that the wave function should be the same here and should be the same here, and we just sort of link them together in a very artistic way, and then we get the solution for the tunneling effect. 好，所以大家会发现这个，在做固态物理研究的时候，有时候你会觉得搞不清楚自己是在做物理还是在做艺术，你就会你就是可以看一下它的那个图案，然后大家就知道它到底做了什么事情。就是它左边呢。1号解1号，它就先假设一个正弦波，然后呢解3号，它也假设一个正弦波，然后经过中间的墙壁的时候，1号正弦波的强度就被削弱了，然后呢，这个削弱的地方它是怎么弯的，怎么转的，那就是薛定谔方程式会解出来的答案。好，所以有时候看个性吧。像我的话，我就会觉得解这个好痛苦因为都觉得搞不清楚那个答案到底是真的还是我的幻想，会觉得有一点点难过。但是如果你是做材料学的，或是你是研究一些材料基本物理的，就是要可以接受这个东西。如果这个东西你觉得OK，你可以接受，或者是你在创造这些。potential energy 的模型很有创造力的话，那你就蛮适合研究材料物理学的。So now actually you can check a little bit about your own abilities. So if you find yourself very creative in building models like this, and maybe you are a very talented material scientist, and you can go for that direction. And now this is the difficult part. But I would like to introduce it anyway. So here's a combination. Now we are comparing the matrix mechanics and the wave equations. So you can see here we have a big table. Oh, I should go faster. So on the left-hand side, we have the wave equations by Schrödinger. And on the left-hand side, we have the matrices developed by Heisenberg. But the basic idea and basic procedure for both of them are exactly the same. So first of all, we have to have a function or matrix to describe the current situation of the system. And in German, it's called Stande. And in English, they translate it into state. But state means that, for example, like now, here, everybody's sitting here and staring at the slide. Here's a Stande, and this is a state. This is the situation. And again, for the particles, here's the situation and a wave function for this situation, and it should be a wave function like this, and it should be a combination of a lot of waves. And for each of the wave, we have the amplitude C1 to Cn, and for each frequencies, we have equations x1 to xn. So this is a generalized wave function for a state, for a quantum state. And in the matrix representation, he defined a new symbol called bracket. So this is bracket, this is bra, this is cat. And every calculation for the possibility is the combination of bra and cat. And so here is the symbol for a state of a system in the form of a matrix. And you can see C1x1 to Cnxn, and in the matrix is C1x1, Cnxn2. So you can see the symmetry between them. You can see why they are just exactly the same thing. Okay, and if I would like to know the probability of a situation, the probability of a state, and then in Schrödinger's wave function, then we just take absolute value and take a square on it, and then we do the summations of all the frequencies, and we just do the summation for all the positions. And after all of these summations, so this is very difficult because you have to do a lot of multiplications with so many different parameters, but here are some rules to follow anyway. But finally, we will have a equation like this. This is all the amplitudes, and here's the summation of all of the amplitudes. And for our solution, we have to ensure the final summation should be always equal to 1. So this is for the wave function. And for the matrix, it works better in this kind of cases. If you have a lot of waves and if you are multiplying between each other, and for the matrix representation, it's easier to operate, because if you operate it with matrix, and then you can have a vertical matrix, you have a horizontal matrix, and then you just do the commutation. I don't remember what is the name in English, but you just do an operation like this, and then dun, you get the answer. Okay, so I think the Schrödinger's wave function is very good at the graphical representation, but if you have a lot of waves combined together, if you have the wave packet, and then it's easier to use the matrix representation. Okay, and then here is the interesting thing. So in reality, if we do a measurement, and how do we represent it with the mathematical equations? So in case of Schrödinger, a measurement is defined by a observable. And now we just assign the observable is a number A. So this is the expectation value of something that we are measuring. And then again we have to do the conjugate of our wave function, multiply it to a, and here's the original wave functions. And because we have a lot of frequencies, so we have I, the index number from 1 to n, and another index number, and then you have to do the multiplications by all the combinations of the index numbers. And here's a lot of complicated combinations, and finally you have the expectation value here. Okay, and this is called operator, and this is called eigenvalue. Eigenvalue is German. Eigen. How can I explain it in English? No explanation. Sorry. 就是 eigenvalue 这件事情，它是德文。eigen 在德文里面就是那个唯一的意思，或是期望的意思。好，然后这很难用英文解释。好，没关系。总之，两个都是德国人，所以我们也没有办法，只能想办法习惯他们的世界观。And in case of the matrix representation, then it's a little bit easier too. So we have the observable. We have we have the bra for the state and ket for the state. And the bracket representation in matrix form is 3 matrices lining up like this, and then you have to do the matrix multiplication, and finally you get the result. And in mathematics we call it eigenvalue. Okay, so now I just try to do the comparison for you. So now you can understand. Oh, so when we are talking about wave function, it's playing around like this, and for the matrix, it's playing around like that. But they are actually doing the same thing. They care about the same thing. They care about the state of the system. They care about the total probability, and they develop a lot of symbols, a lot of operators for different kind of measurements. Okay, 然后再来接下来的事情呢，就是针对各种不同的量测，针对各种不同的观测值，然后理论学家他们就创造出了很多种不同的 observables 跟很多种不同的矩阵。好，这就是后话了，这就是接下来的故事。好，所以如果以后人家在说什么波函数、什么矩阵方程，你就了解是什么回事了，就是这个啦。Okay, and here's the comparison. So here's the wrapped up form, and here's the open up form, and then we just wrap it up together. So the wave function, and here's the operator developed by Schrödinger. Here's the operator for momentum, and you can see the wave function is usually modeled by the oscillations. And this is the operator for energy. By some derivations, and then Schrödinger just decided to use the symbol like this. And then for Heisenberg, he somehow developed or discovered the same. He just noticed the same thing from the spectrum of the hydrogen atom. So he just developed the operator, and you can see that they are very, very similar to each other. So this is the link between the wave mechanics and matrix mechanics. And this is something that I just explained in the chapter of uncertainty. So okay, we'll just leave it that way. And if you are interested, you can read it. But if you really need to understand it, and then you have to learn some linear algebra about matrices, and you have to apply some rules in mathematics of matrices, and you can understand what's going on. But I just skip it that way. Okay, so now we are coming into the most important dilemma in quantum mechanics. So we started from photons and electrons. So here is the original photons, which is going through a double slit, and just behind the double slit, we can see the slit of interference. So we see it for the photons, we see it for electrons, and that is the reason why we can combine the representation for particles and waves. And so we started from photon, we get into electrons, and what if we make the object bigger? Like we have electrons, and what if we have a bunch of particles combined together? And what if the bunch of particles turns into a cell? What if it turns into a virus? What if it turns into an animal? Or what if it turns into human? And why is this kind of interference so obvious in little particles who is running really fast, but it's not obvious anymore for a cat? For example, if you have a cat at home and you have two doors, and of course you're expecting that your cat is walking to one door, and you don't see fringes of your cat after the two doors, right? So now this is one of the obstacles that in quantum mechanics. So for the world with little particles and for the world with bigger objects, and somehow here's a big gap between them. Something in between is something that we don't know. So this is one thing. And to explain the things like this, a Bohr and his friends, usually we call it schools, 学派, in academics. So the Bohr's school, and they just developed a kind of interpretation for it. They just said that all of the mathematical tools, the wave functions, the matrices, and they are just mathematical tools to help us to describe what we see. So let's just stick with the measurable facts. For example, if the wave function works for electrons, then it works. If it doesn't work for the cat, then it doesn't work, and why bother? And if it works for what you want to describe, then this is a good tool. It doesn't mean that you should throw it away. So this is generally what the Copenhagen's interpretation is saying. And they just would like to tell you the wave function here and all the states in the matrices, they are just mathematical tools, and we don't need to care if the wave function really exists or the matrices, what is the physical object which is really related to it. We can separate the tools and the existence. So isn't it very philosophical? 哥本哈根诠释呢，它的意思就是说，哥本哈根诠释它就是一个标准的工具论者，就是他们会觉得，我现在发展出一些模型，我现在发展出一些数学工具，那只要它好用，只要它可以在某种程度上解决我眼睛前面的问题，这就是一个好工具。你不要再纠结了你不要再纠结说我的这个工具我要从你的脚的 particle 到一只猫都可以，就是你的要求太高了。那对哥本哈根诠释的人而言，他觉得说我使用的工具跟我在描述的东西的这是两件事情，你不要硬把这两件事情绑在一起，不要这么纠结。那所以他们就是非常标准的工具论者，他们就觉得说工具好用就好了。那工具跟我描述的东西是不一样的东西，这件事情你不要觉得就是这件事情没有很严重，对他们来讲这件事情不严重。但是对于一些比较钉钉的人会觉得不舒服，他会觉得说我现在用个东西叫 wave function， 但是我在这边算了一堆东西，跟实际上的东西如果完全没有连接的话，他会不安呐。他会觉得说，那我不就在幻想吗？那我的幻想只是刚刚好跟现实都在一起而已啊！我不认为这是科学，我不认为这是对的。所以这个是这两派人他们在吵的事情是这一件 ，OK。And then Bohr just said that here are possibilities. and the particle can exist in different cases, and all of them have different possibilities. And finally, you just see, for example, like electrons, the interference of electrons. And if you really do measurements, and we are counting electrons 1 and 2 and 3 and 4, right? And you see that one specific electron. Photon is really difficult to see a specific one, but for electrons you can see a specific electron. You see that specific electron because you measured it. If you don't do the measurement, then it's just a possibility. So that is the transition from probability to reality. So from both thoughts, in all of the derivations like this, you have to add another operator for measurement, and finally you can get your result. So this is what he is thinking about. But Einstein has a question. He said that, no, this is ridiculous. If something exists, it just exists. And if something happens, it just happens. And the existence or something happen even when you are not staring at it. So Einstein is a little bit more humble at that cases, and he would like to tell you, wow, something, for example, the student like this, and if I'm not looking at him and he still exists, right? It's not like when I'm not looking at him and he just disappeared. This is ridiculous. So this is what Einstein would like to say. This is something wrong. And he actually would like to say that measurement shouldn't decide the outcome. This is philosophically strange. Okay, so this is Einstein's argument, and he is a little bit more serious about it, but Schrödinger is a funny guy, and he would like to tell the story in a more funny way. So he just developed an experiment. This is the very famous, the Schrödinger's cat in a box. So he just said that if I have a cat and if I have a radioactive material here, and when a quantum effect, you can see that the tunneling effect, and it's a quantum effect, and then the particle just hit a sensor, and the sensor just open up the box with poisoning ingredients, and what happens with the cat. And following Copenhagen's interpretations, before you really open the box, you have a living cat and a dead cat. They coexist in that situation, and in the moment that you open the box, you will stare at the cat, decide if it's alive or if it's dead. So he is developing this kind of, it's a little bit like a joke, ironic joke, and he would like to show how ridiculous the Copenhagen's interpretation is. Okay, and he actually would like to tell us the cat is alive or dead is already as it is before you open the box. The observer doesn't decide if the cat is alive or is it dead. 好，所以呢，就是薛定谔他当初讲说这个薛定谔的猫的故事，他其实是在讲一个反串文，就是他自己本身呢其实是觉得哥本哈根诠释非常的荒谬，但是薛定谔比较有幽默感，他就比较不想要像那个爱因斯坦一样，就讲大白话，直接骂你说你怎么这么荒谬，他不想要这样子，所以他就讲了一个搞笑的故事，就像我们现在在那个 Facebook 上面，或是有很多粉丝团，其实都反川普嘛，就是他其实很讨厌川普，可是他就假装他是川普，然后讲很多很荒谬的话。那薛定谔他当初做的事情是一样的哦，所以他讲这个故事，他完全不是认真的，他只是在讲反话而已，所以他想要告诉你说。阿波罗讲的那就是什么哥本哈根诠释，他的意思就是说，你把猫关在盒子里面，然后里面有毒药，然后呢，在那个毒药就是在盒子衰变发生的一刹那就已经释放出来了，然后你从常理来想，就知道猫已经是死了嘛。但是以哥本哈根诠释来讲， 只要你没有把盒子打开，你没有看到那个猫，那个猫就是死的跟活的两个 state 会混在一起，然后呢完全无法决定。然后是你打开了那个盒子，看到那个猫的一瞬间，是你决定的那个猫是活的还是死的。所以他想要用这个反串文跟大家说哥本哈根诠释有多么的荒谬。但是呢，接下来的故事大家都知道了。我们对于这薛定谔猫的诠释很认真诶，就是请你，如果你要打笔战，请你不要用反串文，人家就会当真的。And he was describing it in a very ironic way, and I think the most important story that we learn is if you would like to really give a statement and you just say what you want to say and don't say it ironically because the people can take it really seriously. So people are really serious about the state of the quantum state before the observations, and they are very interested in what exactly is the critical factor that decide the state. Can I see a lot of states at the same time? And then here are a lot of stories. Here are a lot of stories like the coexisted universe, the coherent theory. 接下来就有很多故事啦，就是那个什么多重宇宙，然后去同步化。然后也有一些做实验 ，and then here are some experiment like one of our paper for the final examination is the people who is following the ironic story very seriously. They started from photon, and then do the Schrödinger's cat for electron and for a virus. They are really doing it for a virus, and they would like to analyze the state of the virus before they shoot the laser to the virus. And yeah, so people really take it seriously. So I think now we are more or less at the end of our lecture. So I hope the explanation here can help you really understand what's going on with dilemmas like Copenhagen interpretation and Schrödinger's cat, and now you really understand what's going on. I planned to play the video here. Do you want to see it? We still have 10 minutes. So if you want to leave and if you want to go to the toilet, and then please just help yourself. But I'm playing these videos anyway, and I think this is a very good ending for our courses through the year. Don't wait for a while. 我本来是有准备一个影片想要给大家看，但是其实我们已经超过上课的时间了，所以有事需要先离开的同学，或者想要上厕所的同学就可以先离开，没有关系。但是我会把这个影片放完，有一点长，因为它是个 TED Talk。
Why does the universe exist? Why is there a world? Okay, all right. This is a cosmic mystery. Be solemn. Why is there a world? Why are we in it? Why is there something rather than nothing?